Okay, so this part is on quadcopters, or if you like, drones. I would call them quadcopters because I'm specifically using 4 rotors in my derivation. Okay, so what is a quadcopter? What's a model for a quadcopter? Well, I would like to think that it's something like this. It's basically 2 sticks, okay, and then there is a motor which is represented by these circles or ellipses, whatever you would like to call them, and uh, then we also need to specify a coordinate frame. So this is kind of okay, so this is actually what I am showing is actually a 3-dimensional object on a 2-dimensional surface. So the way I've shown this for this particular uh, quadcopter is that this is going to be the x direction, so that's the x direction, and then y direction is along the other line. So basically this angle is 90 degrees, and then z is going to point upwards, right? Okay, so with that, let me write down, let me draw the axis. I'm going to draw this axis because these ellipses, as I said, represent motors, and those motors are spinning. So what is done in a typical quadcopter is that you spin these motors in a certain direction. Okay, so let's call this the first ellipse, and this one rotates counterclockwise as viewed from top. Okay, the one which is diagonally opposite to 1, let's call it 3, and it also spins in the counterclockwise direction, so that's 3. Now let's call this one as 2, and that actually rotates clockwise in as viewed from the top direction. So, and then this one is the 4th one, and that also spins clockwise as viewed from top. Okay, and the other thing I need to put here is the length. So let's assume that the length of these rods are L, and then of course there's gravity. Okay, so that's my caricature for a drone or quadcopter. Now there are a few things I need to tell you about how this thing is actually working. Okay, why is omega 4, omega 1 the way they are? Okay, okay. So first of all, this is, you can think of this as a 3D object. Okay, a 3D object in space is going to fall down if it is not supporting itself, right? So how does a drone support itself? So gravity is pulling it down and something supports itself. Now this spinning of the motor actually helps it to propel upwards. So what happens is each motor provides an upward thrust, okay, or thrust in the z direction. Okay, and this thrust is actually proportional to omega squared, okay, in this particular configuration. So what we do is there is a coefficient for thrust, which is a b omega squared. So this is the thrust. I think it's called something. Let me check my notes. Sorry, this is, we'll call that k. Okay, and let me just check what it's called. Okay, it's called a lift constant. Okay, now this lift constant is just like mass. Okay, you cannot you cannot derive it from first principles. It comes from measurements. That's like you use a weighing scale to measure mass. So that's something which will be given to you. So in this case, what happens is that thrust, which is the force in the z direction, we call it Fz, is given by the sum of all the squares of the speeds. Okay, and so this thrust Fz is now balancing mg. Okay, that's the idea on how a quadcopter balances itself. It's the thrust provided by uh, this the spinning motors. Okay, so that's one part. So Fz is the force in the z direction. Okay, now these individual motors also allow the quadcopter to basically rotate about its axis rotate about the x-axis, rotate about the y-axis, and rotate about the z-axis. So let's call that rotation as tau x. Rotation about y is tau y, and rotation about z is tau z. Okay, and these rotations come because these motors can be spun in the way you want. So uh, here's how these torques appear. Okay, so if you see, so what's the best way? So let's try to see how tau x comes. Okay, so tau x, as I said, is the rotation about the x-axis. Okay, so in order to rotate about the x-axis, what I need to do is, see, this is the x-axis, so I need to rotate about this axis. Okay, so let me redraw the figure here. This is the x-axis, and I'm only going to draw these two motors, the omega 2 and omega 4, and they are spinning in that direction. But what's important is that they are generating a thrust which is equal to omega b times k times omega 2 squared, which comes from here, right? And this one is generating a thrust of k times omega 4 squared. So in order to spin about the x-axis, what needs to happen is, if you spin the one of them, omega 2, faster than omega 4, then you will see that this quadcopter actually spins about the x-axis, and that's basically the whole idea, which is, so actually I showed this in the opposite direction. It should be counterclockwise when viewed along the positive x-axis, so it should be this way. So then tau x is given by k omega 4 square minus omega 2 square, but that's the difference in the force. You still need to multiply with the lever arm, which is basically the distance between the two motors, which is in this case L. So that's how the quadcopter is able to spin about the x-axis. If you want to spin about the y-axis, then the same logic applies for the y-axis. Now I'm going to now draw omega, see, omega 1, omega 3, then these are not important, we just not draw them. And so then I'm trying to see rotation about the y-axis, which is in this case pointing, the positive y is this way, so this way. And then, as I said, this one generates a thrust of p, or sorry, why am I saying p again? It's just k times omega 1 square, and then k times omega 3 square. And so the net thrust, so what's tau y? It's basically the net thrust, or k times omega 3 square minus omega 1 square times the momentum, which is L. So that's how the quadcopter can sort of spin about the y-axis. Okay, so I've got tau x, tau y. I'm still missing how it's yaws or rotates about the z-axis, and I'll just do that in a bit. But is this clear? Any questions on this? Okay, let's go to the next page, and now let's see how to get the equation for tau z. So in case of tau z, it's basically, there's a different constant. It's basically tau z is given by b times omega 1 square minus omega 2 square plus omega 3 square minus omega 4 square. It's basically the net spin. So you can think of, so if you, me redraw the figure here, if you look at the quadcopter, I showed you that omega 1 is this way, omega 4 is the other way, omega 2 is also this way, and omega 3 is counterclockwise as viewed from up. So what this equation is saying is that uh, the net yaw or rotation about the z-axis is of because there are motors spinning in opposite direction. So these two induce rotation which is in the positive z direction, so that's why they have a positive sign. But then omega 4 and omega 2 induce rotation in the opposite direction, right, because they're spinning opposite direction here. Omega 2 and omega 4, they are clockwise viewed from top, and the difference between the two is what is causing the yaw. And this constant b is actually a different constant, not k. So it's not the same phenomenon which is causing the lift. It's the lift is only due to moving the object moving up or down, but here there's a new constant b, and it's actually called the drag constant, which is an empirical factor which is found from doing an experiment. Okay, so those are the external torques induced by these motors. So there are 4 of those, right? So to summarize, the spinning of the motors induces these 4 things. One is it induces a force in the z direction, okay, force in z. And then second and third and fourth is going to be the torque in the x, torque in the y, torque in the z. So these are torques in x, y, z direction. So what's interesting to note is you can perfectly induce rotation motion. Okay, you can induce torques in x, y, z. You can only induce force in the z direction. You cannot induce fy and fz, sorry, fy and fx directly, right? Because there is no way these motors have that capability, because the way they are mounted, they cannot induce a force in the xy direction. However, if you want the quadcopter to move along the x and y axis, what you need to do is you need to basically rotate the quadcopter a little bit by an angle, okay, about the x or y, and then the force will actually be, this force, by the way, is along the gravity axis, right? If z is upwards, the moment you rotate the quadcopter about the x and or y, you will actually have the force acting in a direction which is other than the z direction. It's actually going to be, a component is going to act along x, and maybe a component will act along y, and another component will act along z, and that way you can indirectly induce motion in the x and the y direction by rotating the quadcopter. Then the question is, how do you rotate the quadcopter? Well, these torques actually help to rotate the quadcopter because they are inducing only rotational motion. So that's the idea. So controlling a quadcopter is a bit hard because you cannot directly influence two directions. You need to indirectly get them by first inducing a rotation, and then the force will then point the right direction. So another other way to think of this is, we have 4 control variables. What are those? Well, they are the angular speeds. You can spin the motors the way you want. But the concern is we have to control 6 numbers. And what are the 6 numbers? Well, they are the position along x, position along y, position along z, right? You want the quadcopter to go from point A to point B, and also the orientation. Some task, like for example, there is that stick in that video I showed you, that stick has to be vertical. And so the quadcopter has to be obviously have theta, phi, and psi equal to 0. So we need to control 6 numbers. However, we only have control over only 4 numbers. So that's where the control challenge is. So that's why controlling quadcopters is perhaps more challenging than controlling a manipulator, where you have one joint and you have a motor, and here you have only 4 motors, but you're trying to control 6 numbers. Okay, so that is sort of the overview on how a quadcopter is sort of controlled in a very generic sense, and why controlling a quadcopter is hard. So question. Okay, so there's a question. So to get the Fy first, get tau, and then apply the Fz. Well, not so. The question was basically, if you want to get Fy and Fz, how to get Fy and Fz, sorry, Fy and Fx. Okay, so what I was saying is the quadcopter in its original configuration is like this. Okay, its Z is like this, and so and all the forces acting in the Z direction balancing mg. If you want to get So to get any of these forces, what you will do is you'll actually apply a torque. Okay, let's say you want to find a force in X. Sorry, try it with a different color. Y and Z. Okay, so this is Fz. Now, if you want to have a force in this direction, then you want to rotate the quadcopter by an angle. So the quadcopter in the new configuration says like this. Sometimes very hard to draw these 3D figures. Let's see. So then the axes are like this. And so think of almost turning your head when you do this. So now the quadcopter has turned. And now this force is no longer, well, it is Fz, which is acting 90 degrees to the plane of the quadcopter. However, now it has a force in the up direction and possibly a force in the X direction. So yeah, so you need to Fz, let me call it Z prime. So this force is in the body frame. So body frame, things are always oriented in the same direction to the axis of the object. But once you turn it, now the force in the world frame is going to be a component of Fz, right? Fz cosine, if you think that's the angle, and then Fx will be Fz sine if this is a simple rotation. So that's how you get it. So yeah, so you're right. So you need to first induce a rotation, activate one of those torques, rotate it, and then induce motion in the X or Y direction. Okay, let's see how we're doing on time. It's 45. Okay, so I wanted to go ahead and derive the equations, but that will take me more than 5 minutes. What I'll do is I'll stop here, and maybe, you know what, let me just stop here. Last I talked about quadcopters and essentially didn't do derivations, but I showed you the thinking behind uh, arranging the motors on a quadcopter. So there are essentially 4 motors, as you can see in this picture. 2 of them are spinning clockwise when viewed from top. Okay, two from the clockwise, like you see here, W2 and W4, and 2 of them counterclockwise, omega 1, omega 3. And because of this particular way in which they are configured to spin, we have four external forces or torques on the system. There is a thrust force which is keeping the quadcopter flying in the air. That one balances the force due to gravity. And then there is torque about x-axis, torque about y-axis, which can help the robot to pitch about the x and y-axis. And then the fourth one is tau z, which basically helps the quadcopter to spin about the z-axis. So what the way I stopped saying that, stopped with the comment that although you have 4 things you need to control. Sorry, six things you want to control, which is the three positions and three angles. You only have four control inputs because there are four motors, and you can only control F, Z, tau X, tau Y, tau Z. And in order to control the X, Y dot and X dot, which are clearly not part of these forces, then you'll have to first tilt the quadcopter by applying a torque, and then FZ comes out to be at an angle, which means that now it can influence the force in the X and Y direction. So this is the theory, but let's now look at how to derive the equations for the quadcopter. So I'll do that using Euler-Lagrange method. I'm going to follow Euler-Lagrange method. First, we need to establish the positions of different um, links. In this case, there's only one link, that's the quadcopter, which has the X, Y, Z for its position, linear position. And then we going to express the rotations in terms of theta, sorry, phi, which is along x-axis, theta along y-axis, and psi along the z-axis. So those are the Euler angles. Next, we need to find the velocities, which is simply x dot, y dot, z dot. And then even though we would like them to be phi dot, theta dot, psi dot, that does not really correspond to the angular speeds of the quadcopter, because the angular speed is given by a different formula, and I wrote it down in the body frame. So there's omega x, omega b y, omega b z, where this b indicates body frame. I wrote that just because we know the inertia is in the body frame, and that will help us to write the kinetic energy for the system. So this formula here is in terms of the rotation matrix, which can be essentially simplified to this simple form: cosine phi minus sine phi cos theta sine phi cos phi cos theta, and then phi dot theta dot omega dot, sorry, my bad, this is psi dot. Okay, so those are the Euler rates. Okay, so we have the angular speed. Let's now write the kinetic and potential energy. So step 2 is the kinetic energy is half mass, let's assume is the mass, times the velocity, which is x dot square, y dot square plus z dot square, plus half the inertia about the x-axis. So when we say the inertia here, I'm assuming it's the principal, it's along the principal axis, and the principal axis are the x and y and z I showed in my earlier figure. That actually comes from your CAD. If you have if you design this system in CAD, the inertia which the CAD will give you is by default the inertia about the principal axis, and that's the one you want to use. So ix omega bx square plus iy omega by square plus ic omega bz square. Okay, and then the potential energy is simply the one due to gravity, mg times z, and then the Lagrangian is the kinetic energy. Actually, my bad. I usually write this as t, right, and then I write this as v. So t minus v. And so once you get that, deriving the equations is very easy. It's just writing the Euler-Lagrange equation. So it's dl dq dot, let's put j, minus dl dq dot j equals, now here for the falling body there was no external forces, right? But in the case of a quadcopter, there are external forces and torques, and they should be written down in on the right hand side in this equation. So what are these q's and tau? Well, qj, or q rather, is x, y, z phi theta psi. Okay, and the capital tau is basically the six external forces. So those are the external forces acting in the x, y, and z direction, so linear forces, and then the torques, which is x along the x, y, and z axis. And I have to pretty much write these down so that then I can put them in the equation. So let's see how do we get. So this part is very clear. This is very easy to find the left hand side of this equation. We've done it numerous times. The right hand side is the one which is less obvious. So let's see how to write the equations for capital tau. So next is, first let's write tau, because we already wrote them, right? Tau external is going to be tau about the x we wrote down, tau about y, tau about z, or you can think of them as tau about phi about theta, tau about psi. Okay, so those are something we wrote down previously. It's the constant k times L times omega 4 square minus omega 2 square, and then k times L omega 3 square minus omega 1 square, and then finally b, I think it's the drag constant, omega 1 square minus omega 2 square plus omega 3 square minus omega 4 square. Okay, where k is the lift constant, and b is the drag constant, and these are found experimentally. Okay, so that's the torque. That was easy. We need to find the force. Okay, now the force is a little bit trickier. What I showed you here in this figure was this force acts in the z direction, right? It only acts like so when the quadcopter is perfectly aligned with the z-axis. When the quadcopter rotates about the x-y-z axis, that force has to be basically resolved along the x, y, and z direction. So this force, uh, we basically need to write the force essentially in the body frame. So what we need to do here is, this is similar to how we did. So if you remember, we had a vector in body frame, and then we had a vector in fixed frame. Okay. In order to find the relation between body frame and fixed frame, we rotated by the rotation matrix R, right? Because the force is, well, in this case, we are trying to sort of express the force from one frame to another. The force Fz really depends. So the force basically is acting along the z always, but as the quadcopter tilts, it's going to have a different effect than it would be when the quadcopter is perfectly aligned with Fz. So what I need to do here is I essentially need to write R times the thrust minus, I'm actually including another force called drag force, which I've not written down so far. And so this is just assuming that there is a drag force acting along the XYZ direction, which is very similar to the drag force we saw in the projectile problem. If you remember, that was quite a while back, where we had a quadratic drag. So this is a common term they include in modeling a quadcopter, because when a quadcopter moves, it's moving fast, and when it moves fast, the drag force sometimes cannot be ignored. So I'm going to write it down that way, but when we do the simulations, we have the option of turning it on or off. So then what we need to do here is write a rotation matrix, which is this complicated thing, which I will not even bother writing here. I will do that in the symbolic derivation though, times the force or thrust force, which is 0 along the x, 0 along the y, and it's k times omega 1 square plus omega 2 square plus omega 3 square plus omega 4 square minus this drag force. This is something which is again found empirically. Here I'm assuming that the drag force is linear in velocity. So you can see there's a sort of a damping term times velocity. Ax is the damping constant in the x direction, ay is the damping constant in the y direction, and az is the damping constant in the z direction. So what this uh, R is doing is it's taking this force, which is in the world frame, and convert it into the force in the body frame. So once we get this, we have capital tau, which is F external and tau external, which we wrote down. And so all that remains to be done is to take this in Matlab, or whichever package you want to use it to derive the equations, and write it as, so simplify the equations to this form. A capital X equals B, where A is a 6 by 6 matrix, which is linear in, so A times X equals B. So X here is the acceleration. So X double dot Y double dot Z double dot theta double, sorry, phi double dot. We need to be careful about the order. Theta double dot and psi double dot. And so A is all the terms which are linear in acceleration, and then B is a 6 times 1 vector which has the gravity terms. It has what you might have heard of centripetal forces and Coriolis forces. So these are typically square in the acceleration. It will also have the drag forces, which in case you want to keep them, and then there'll be all these external forces. So B has centripetal force, gravity, external force, and a Coriolis force. And it could also have the external force that includes the drag, but if you want, I can just write a drag force. So all those things are on the right. So that way you can, by changing B, how do you change B? Well, you have control over this capital tau through the external force, because you can control these speeds. You can influence the B, and hence you can influence the accelerations, and that's how you control the quadcopter. Different from that earlier code. So similar to the previous code, there's a rotation matrix. I define the angular velocity. Okay. Instead of writing that equation with the matrix, I actually did the calculations here. The kinetic energy, the potential energy, and then the Lagrangian, which is T minus V. And then I define the thrust force, the drag force, and then the external force, just like the equations I wrote down on paper. Okay. So once I have those, I have tau external, I essentially crank the Euler-Lagrange equations just by doing this formula, which I've been doing in the past. The only change here is that this tau external should now go inside this equation. So instead of writing it to the right, I moved it to the left. So I get a minus sign, and all that should be equal to 0. So simplifying, doing some simplification, I can end up with the acceleration x, which is a divided by a inverse times b. So if you run this, it spits out the a and b matrices, which I then take and copy into the right hand side, which I think in this case I wrote down right here. So I call it EOM, which is equations of motion, and they are all copy pasted here. So copy pasted from. Okay, so With that, I can do a simulation animation. So define the constants. I just found some constants from the internet. I put them in the equations. So you can see that this constant k is actually very close to zero. It's very insignificant. Here b is also very close to zero. So if you want this to really have an effect on the system dynamics, you remember that k multiplies with omega squared. So you need to really spin the motors really fast in order to have any substantial effect. So if you have, for example, 100, then 100 square is going to be um, four zeros, and there are six zeros here, so that's going to be 0.01, which may be quite insignificant. So you want to ensure that it's probably something like 1,000 or something, the angular speed, in order to have any effect. Okay, so that's why you see these quadcopters spinning their motors very fast. You don't see them going very slow. You need to generate all that lift using your own motors. So here what I did was I actually set the speed to zero just to start with. Okay, speed is zero, and let's see what happens. So clearly, if the speed is zero, then the quadcopter is going to sink, it's going to fall. So what we need to do is we need to find a speed, okay, keep everything as zero. We need to find the speed such that the upward force is equal to the force due to gravity, and so the quadcopter can stay in there. So what I actually did was, this is actually my way of cheating to get the speed. I just divided by 1 over k, and that's just ensuring that that k factor is out of is really going to be normalized, and so I don't have to just worry about changing the speed. So here uh, I actually have 1.075, that's where it works, but let's try 1, and then you should see that the force is not enough for the quadcopter to stay. So it sank in the ground, but not that fast as it did without any force. So now if you do it 1.2 and you run this, then you'll see the quadcopter is actually flying up. It's flying pretty fast. That's why the x and the z axis actually scale based on that. That's a little bit too high. So let's try 1.1. And now you can see it's sort of slowly drifting towards there, but that's slower. Anyway, so I found that about 0.75 is about right for the speed. So it's not really 1.075, it's times this, right? 1 divided by that. So that's, you can see it's 1 in -6. So that's like a factor of 10 raised to 6. That's really fast speed. That's the real speed, which is 1 e raised to 6. Okay, so let's run this. And now you should see that it is hovering. It's not moving up or down. Maybe there's slight motion in there. So then it's kind of important before you start working with a quadcopter to ensure that the speeds of all the motors are set to so that the quadcopter can balance itself in there. That's the first thing to do. Once you do that, then, as I said, one way of ensuring that the quadcopter rotates about the axis is to actually put a differential speed on two of those wheels, right? So, for example, if I put a differential here, so I have a d speed, and I'm going to change the speed of omega 1 and omega 3, which happen to be the 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 motors which are spinning in the counterclockwise direction when viewed from top. So the effect they have is, if you look at the equations, the effect they have is they change tau along the y-axis, because tau along the y-axis is omega 3 square minus omega 1 square. So let's see what happens. Sorry, my bad. My bad. So they actually won't change. I should pull out the equations. Let me pull out the equations I need. Okay, so here we can see that there is, what we did here effectively was we set the angular speed so that this factor was just equal to mg, which is not shown here. But now we're trying to control the pitch of the quadcopter based on these three equations. Okay, so if I want the quadcopter to rotate about the z-axis, I want to ensure that z is actually psi. Then I want to ensure that these taus are zero. So the way I can ensure this taus are zero is omega 2 should be equal to omega 4, and omega 1 should be equal to omega 3. But then the spin is because omega 1 and omega 3 are different from omega 2 and omega 4, because that factor is subtracted. So if you want the quadcopter to yaw or spin about the z-axis, then you need to change omega 1 and omega 3. And that's what I'm doing here, changing omega 1 and omega 3. So let's see what happens. So you can see that the quadcopter is yawing, and it's also falling down, because what's going on there is, if you look at the equations again, since I changed omega 3 and omega 1, that force is now less than that due to gravity, and so it's going to fall down. So if you want the quadcopter to spin about the axis and also hover in the air, then you have to proportionately increase omega 2 and omega 4. So one way to doing this is, I think, is 0.5 times speed. Okay, and then you have an equal and opposite one for omega 2 and omega 4. I believe this will make it hover and as well as spin. Let's see what happens. Yeah, so now it's spinning about the axis, but it is not falling down. So this is just looking at the equations for tau. You can make this intuitive thing. So you can see it's kind of getting easy to control the quadcopter when you think of these motors in terms of these equations, just these three equations, right? And of course, the fourth one is that one. Okay, so I got this to spin about the z-axis and hover. Now let's see the effect of these two. Okay, so what I need to do is I need to change omega 1 relative to omega 3 for the quadcopter to turn about the y-axis. Okay, so let me now go back, revert back, and let me just save this. So I'll say that to hover and spin about z-axis, this is what you do. So when you get this file, you can play with this. Okay, so now I'm going to go back to hovering. Okay, just confirm that it is hovering and not spinning. Okay, now as per that equation, which I'll show again, I need to change omega 1 relative to omega 3. So I'll just introduce the differential between omega 1 and omega 3. Okay, so when I do that, let's say this one, d speed, okay, and then run this. So you can see that it's actually falling down, and it actually twisted about the y-axis, right? It was turning. If you saw it along this axis, then it was actually turning about that axis as per those equations. So again, here it's turning about the y-axis, and it actually crashes, and that's because, again, as I said, when you change omega 1 or omega 3 relative to omega 1, you are inducing motion about the y-axis, but it's also causing this factor to decrease relative to gravity, and so the quadcopter will not hover, but it will crash into the ground. So then you got to think of how you're going to adjust the other parameters, so that way you only get one effect, which is that of spinning, and not going crashing into the ground or hovering or going up in the sky. So that's rotation about y. So I will not do the second part, which is how do you hover and make it spin, but that's something you can figure out. And then the last thing I need to do is probably change omega 2 relative to omega 4 to get it to spin about the x-axis. Okay, now you can see it's spinning about the x-axis and it crashes. The same reasoning applies. I'm changing this. The difference here is not equal to 0, and that's why the spin about the x-axis. And then this factor is not equal to that due to gravity, so it's crashing in the ground. And I think there's a slight yaw here, because omega 4 is less than omega 3, right? Omega 2 is same as omega 1, but there is a slight yaw. You did not see the yaw so much because it was very, very minimal. So it looks like what's happening here is there is you lose the hovering capability, you do yaw. So you do pitch about the x-axis, but then you also tend to yaw. So this is like a challenge, which is what you change one variable, you get something else which you don't want, and then you'll have to adjust all three things. So controlling a quadcopter is really having this understanding on what variables affects what, and that I think you can do by simply looking at these four equations, just those four equations. Okay, and there are ways to tune these speeds so that you get what you want. Okay,